Hello and welcome to another control lecture. In this lecture we're going to look at the least squares method of system identification. So after this lecture you should be able to explain the reason behind why we're undertaking system identification and why it's useful and important in the engineering sector and the various types, and also explain the procedure behind undertaking least squares. So what is system identification? System identification methods we can use to develop a mathematical model of our system. So if we've got known input data and captured or measured output data, we can effectively develop a mathematical model. So based on the previous lecture where we looked at the ARCS model, where we kind of put it into this form where you could see that you had an equation that represented past known and measured input and output data, and then we had four known coefficients. So you'll see in this video how we start off from that point, and then we develop a kind of least squares, which is a system identification method to effectively estimate what the coefficients are of that model, which relate back to your system, which are your system model. So such methods. So if we've got a mathematical model of the system, what we can then do in simulation is tune our PID controller and develop control strategies in simulation, and kind of first of all highlight any issues that there might be within the kind of the system in simulation. So if you remember back to one of the early lectures where we were looking at model-based design for embedded control, and I introduced this idea whereby you had this design stage where you used model and simulation initially to get an idea in terms of how your system or your control system was going to work. And that step was introduced in this model-based design approach before you get onto implementation to kind of save error, to reduce kind of risk, those sort of things, and to kind of really to highlight any potential issues that you might have in the system that you're designing. So I think it's very important, this modelling and simulation, so to develop a mathematical model of the system. Within this lecture series, the systems and the models that we're looking at aren't as complicated as you would if you were to an industry where the models would be of very high complexity, lots of kind of input outputs and different blocks representing system dynamics. Within this course, they were just looking relatively simple. So like I said, you can use it once you've got a system model. You could then effectively design your control system and then introduce some of the practical elements that we spoke about earlier, and such things such as what if scenarios. So what if you do this? Can the system compensate for this disturbance? Those sort of things. And if we're talking more about advanced control methods, so we could start looking at kind of the advanced control methods such as the Smith predictor, which is effectively a control system that compensates for when you've got a large transport delay. So, for example, in heating systems, where the sensor and the actuator might be separated by a distance, so the actuator takes action and it takes the sensor quite some time to pick up the effect of the actuator. And that's something we're going to talk about in the next couple of lectures. And also model predictive control, so the idea of predicting the head rather than having a PID controller, which is a control system that effectively reacts based on an error. And that's something, again, we're going to talk about a little bit in the next few lectures. So in terms of different structures of system identification, so you have white, grey and black box models. So white box models, that's pretty much what we're going to look at in this. It's kind of when you know the form of the mathematical model, and by looking at it you can pretty much determine, if you put an input into it by just looking at the form of the mathematical model, what you would expect in terms of the outcome. So it's kind of like its outcomes are kind of precisely determined, and there's not that much uncertainty really in terms of the model. So if you're thinking kind of about a physical model, it could be something like a mass spring damper model. So we've got your mass spring damper, or it could be something like an RC circuit where you've got your resistor and your capacitor. Black box models are where you have pretty much no information of the actual system, and all you have is input and output data. And then grey boxes somewhere in between, where you might have a little bit of prior knowledge of the system in terms of its physical form, but you don't have too much, and you also have some data from the system. So just to note that all models are approximations, and measured data obviously contains measurement error, so it's got noise on it, so that also reduces your accuracy. Also, a lot of systems in the real world are also non-linear. So at the moment we're just looking at linear methods, but you just got to be aware that in the world, a lot of the systems are actually non-linear. So you perhaps need to look at further methods. So if we're just looking at kind of what we've done so far, so an observation. So if you were to apply a U of k, so if U of k and G of z are known, well, in this case it's a continuous system, but it could be G of z, it could be G of s. So if these are known, so you know what the input is, you know what the system is, what we've done pretty much using simulation and theory is we've been able to predict what the outcome is. So in this case, y of k. I'm saying y of k because this is the measured or the sampled output. So if U of k is known, okay, U of k is known, and y of k is measured, then we can effectively estimate what G of z is, obviously subject to having some measurement noise. And then something that's perhaps a little bit more complicated, but if y of k is measured, so we know the system output, and we've got an estimate of G of z, then it's possible then to actually estimate what U of k is. So a powerful observation, it's possible to predict the values of y of k, y subscript k given U of k, and the z form transfer function G of z. If that's possible, okay, then it should also be possible to determine G of z, hence G of s, like I said, from past samples of y of k given U of k, and with knowledge of the sampling interval. So if we just now go back to when we're looking at the ARCS model, so when we had this general second order system where you can see here we've effectively divided through by the highest power to get it into this form, so G of z minus 1. We rearranged it to get it into this form, and then rearranging using the backward time shift operator, we end up with this form here, the ARCS model. So if you're not sure about where this has come from, re-watch the previous video on the ARCS model. So provided we have the current measurement, so y of k, and the past measurement, y of k minus 1 and y of k minus 2, and the known inputs, u of k minus 1 and u of k minus 2, then it should be possible to determine what A1, A2, B0 and B1 on. And to be able to do that in theory, we've got 4 unknowns here. So what we need is 4 linearly independent equation. So this effectively means we need 4 snapshots in time. So y of k minus 1, y of k minus 2, y of k minus 3 for the samples, for us to be able to effectively estimate what these coefficients are. However, in reality, something I'll talk about and notify you a few times. In reality, you'll need a few more data points, or a few more than four kind of snapshots, because you have measurement noise on the signal, and there's a few other things that we'll talk about. So this is effectively what I spoke about, where you've got y of k minus 1, y of k minus 2, and y of k minus 3. So you'll see u of k here that relates to the sample data control system, and then G of z, and then what you'll notice here, y of k. So this is effectively our sampled output measured by the sensor. And you can see here, and this is our sampled u of k going into the G of z. So you can see here all the current and past information, and then here the measurements. And what you'll notice in terms of the pattern, you can see here these are your y of k's and these are your u of k's, your outputs and inputs. And then we've got here E, which is noise. But what you'll notice is you've got k, y of k minus 1, k minus 2, k minus 3, k minus 4. And what you'll notice is the same pattern here appears for this here in the inputs. And then you'll notice here you've got y of k minus 2, 3, 4, and 5. And the same pattern appears here for your inputs. And what we can do then is then put it into this matrix and vector form. So you can see here we've effectively just created this vector here of A1, A2, B0, and B1. So you can relate to these coefficients here, obviously for all these, put them into this form. So this gives us the following form. So here y, which is your output, is equal to phi multiplied by theta. So if we multiply by the inverse of phi on both sides, this gives us this. And what you'll notice obviously is that and that, they're just going to disappear. And then what we've got is theta is equal to this. And what I'm going to add on, because what we're trying to do is we're effectively trying to estimate what these coefficients are. So what I've done in terms of what we do in terms of the notation is put this hat on here. So the hat notation is effectively denotes estimate. So we can say that the theta estimate is equal to the inverse phi multiplied by y, where phi is effectively, you can see here, all these past measured and known inputs and outputs, and then y is our effectively our measured output. So note that the 4x4 it's a square matrix, and the number is the minimum required that we'd need in theory to be able to estimate what these four coefficients are. However, this is impractical as you have measurement noise, and you'll just notice there I've actually just ignored the measurement noise. So, in other words, the unknown coefficient of GZ may be estimated. That's what we're trying to do. In practice, however, the phi, which has got all your measured inputs and outputs, may be ill-conditioned, such that the inverse phi may not exist. Because what you might have is it kind of, for example, the system being in a well-regulated condition, so your measured outputs here being all equal. Likewise for your inputs that you put into the system, again, these being equal. And hence you've got no new information. So it wouldn't really help you in terms of estimating what the four coefficients are. So consequently, the concept taking many more equations than the theoretical numbers here, so 4, leads to the idea of obtaining an estimate of the unknown coefficient in a least squares sense. However, what this ends up doing is, because if you go back here at the moment it's obviously a 4x4, if you capture more and more data, so you can imagine like that, so then you can, allowing you then to be able to estimate what those coefficients are, you end up then with a rectangular matrix. And the issue with that is that then when you come to applying the equation, you can't effectively invert it. And so this, like I say, this leads us on to this least squares. And least squares, it's what it effectively is, it's the kind of like fitting the best line through a series of points. So here you've got input and output, and here you can see it looks like that's the line of best fit. So in terms of how it works, I'm not going to go through the derivation, but what it's effectively doing is it's trying to find a minimum in terms of a quadratic cost function. And the minimum is when these, you can see here D1 all the way up to D6, it's when the sum of these, in terms of sum of between 1 and n, in this case n6, the sum of these D, and when you square them, it's the minimum effectively of that, and that's what it's trying to do. It's trying to effectively give you the best fit to the data. That's effectively what the least squares is doing. So just to continue on what I said previously, so this is the equation we had, and where now n is much greater than 4, so typically it might be 40, and like we said, you end up with this rectangular matrix where you can see the general notation here. So theta is given by that, as we saw, and then the problem is, as I said previously, the problem now is how to invert a rectangular matrix. So again, as I said, I'm not going to go on to through the derivation, but if you look at the derivation, you'll come up with this least squares equation here, where effectively this now becomes a square matrix again. So you can effectively take the inverse of that. So theta hat, which is our estimate, is effectively equal to this phi transpose multiplied by phi, and then this all in brackets, the inverse of that multiplied by phi transpose, multiplied by this vector containing the past outputs. So as previously, this phi hat is the estimated parameter vector, and here is your what it's known as is your observation matrix, whose rows are the observation vectors. And then there's a few little things here that you could know. So the information matrix, phi transpose multiplied by phi, covariance matrix is effectively this. Yeah, and that's pretty much the equation that you use for least squares. There are, when you get onto MATLAB, there's different forms that you can put that into MATLAB, but that there is your least squares equation. So based on kind of having all this information in terms of populating the past measured outputs and the past known inputs, and here your phi, and also your containing your past outputs, you can effectively determine what the coefficients are of your model. So if we go back to the form, so the general form, so where A1, A2, B0 and B1 are estimated, these can be placed into various forms. So what I've got is a short MATLAB demo just to show you a least square script, and I've also got some practicals, so make sure you have a look at them. So the transfer function can be constructed like this. So once you've determined these coefficients, you can see here A1, A2, B0 and B1. So whether you put it into this form, so g of z minus 1 or g of z, you can see here these are mathematically equal in terms of simulation. You'll get the same result when you're simulating the two of them. Or into the autoregression, the ARCS model I'm going to call it, you'll also be able to see how the coefficients relate back to that as well. Okay, and that's quite useful to kind of, to recall against A1, A2, B0 and B1. So these three equations are all very useful once you've determined the coefficients, and you'll see these used in various forms within the MATLAB and the practical that we look at. So in the quality of the estimate in terms of the four coefficients, so in terms of the accuracy, will depend on the quality of the measured data. So if your data has a lot of noise on, your estimate is not going to be perhaps as great as it would be if you didn't have that noise. So if you had your minimum noise. So if the data is noisy, what you really need to do is to capture more data. So you need to increase n. N being your number of data points. So I've got a couple of exercises for you to have a go at here. So what I want you to do is explain the following methods of system identification. So white box models, black box models, and grey box models. Exercise 2, explain the reason behind deploying the system identification method of least squares. So go back to the start of the lecture and kind of revisit that, and then explain the process behind undertaking least squares. So just effectively tell me the flow of the mathematics. So in terms of summary, you've been introduced to system identification and the idea behind developing mathematical models based on kind of known and measured information, so known inputs and measured outputs. I've introduced you to least squares with the use of the ARCS model, and least squares is a method, as I said, building on the previous point, to develop system models based on having kind of information on data, input output data, and just to kind of recall the number of samples of measured error, i.e. noise, alter the quality of the estimated model. So if you've got a system with a lot of noise, you need to take more measurements. So I hope in terms of this lecture you can now kind of explain the reason behind undertaking system identification, and I'd say it's very, very important in terms of industry. So if you go back and watch the first video, there was a couple of the case studies I spoke about where it was the industry were using system identification to develop mathematical models of systems or subsystems. And by now you should be able to explain the procedure behind undertaking least squares. So if you have any questions, please feel free to contact. All right, thank you.